All right, my friends, here we are, and we are going to do synthetic and extraterrestrial diamonds. This is Tuesday's lecture, and I'm actually throwing in a little extra, and we're going to also talk about diamond simulants in this lecture as well. And so this is Tuesday, February. Oh, good grief, we're in February, February 3rd, while I am in Tucson. So I hope you guys are having a great time. I hope all is well. And let's jump in, all right? So just to remind us where we are, we're doing diamond synthetics. And actually, I moved simulants up into here because I wanted to spend a little bit more time on diamond mining. So that's what I did. Um, and our exam is going to start a week from the day this lecture was supposed to be. So basically, it starts on Tuesday, February 10th. And you will have between Thursday, February 10th, to Saturday, February 14th. This is an online exam, and it is in two parts. The first part is multiple choice, true, false, matching, etc. And the second part is our essay questions. So basically, here's the information. We start as soon as class ends on Tuesday, and Tuesday will be the review. On Saturday, the 14th, you have to have everything done by 11:59 p.m. because that's when it closes. This will cover all the diamond lectures and anything we have covered in labs. It's going to be in two parts, all right? So part one must be taken first. You must completely finish part one before you start taking part two. However, with both of these, when you start taking part one, you can save, exit, and return to part one. And when you are all the way done and have uploaded part one, submitted part one on Learning Suite, then you can go to part two and you can start on that and you can save, exit, and return. But with part two, you absolutely cannot look at any of your notes or talk to anybody about anything because part two is closed book. So part one is open book, open slides, open notes, open internet type stuff. It is closed AI. Okay? Do not use AI to answer these questions, please. Part two, though, is completely closed. You are not able to use anything but your own brain. Okay, so hopefully that makes sense. If not, come talk to one of the TAs, send me an email or a text, and I will get back to you in the evenings of the week that I am gone. All right. Well, let's start talking about synthetic and extraterrestrial diamonds. Okay. So these are diamonds that are real, true diamonds. They are they are natural. That's not the right way to say that. Let's try that again. They are real diamonds. They are the same as natural diamonds or mined diamonds. However, they are formed in a different way. So with synthetic, they're formed in a lab, and in extraterrestrial, they're formed in, well, outer space or on other planets and things like that. So synthetic diamonds are fundamentally the same as natural diamonds. They aren't fakes. There's two different kinds of synthetic diamonds that are common today. So we have what are called high pressure, high temperature, which is HPHT, and we have chemical vapor deposition, and those are called CVD. Now, again, remember that, sorry, it's not moving forward. Why is it frozen? That was weird. Okay. Remember that lab created diamonds, even though they are fundamentally the same and they are considered real diamonds, can be distinguished from natural diamonds. We can tell the difference between a mined diamond and a synthetic diamond or a lab created diamond due to unusual growth features, unique inclusions, and things like that. And we'll talk about that. And then the other thing I want you to keep in mind for your key points is that diamonds can be created by meteor impact on Earth and in certain situations on planets outside of our solar system and possibly even inside of our solar system, though that's a little dicey still. So let's talk about the origin of diamonds. We have our mantle formation. That's 99% of our diamonds. That's the stuff we've been talking about forever. Lithospheric diamonds, the ones that are in the lithospheric mantle, cratonic lithosphere, whatever you want to call it. 99% of all mined diamonds are from there. Subduction formation diamonds, they are beneath the lithosphere. They are actually in the mantle, and they are about 1% of all mined diamonds. Those are the clipper diamonds, the super deeps. And really, it goes between 1 and 2% of all mined diamonds, depending on who you read. And then we get laboratory formation or man-made, synthetic. There's a lot of different names for it. And it has about 20% of the market share right now. It is expected to go up, but it is not expected to completely overtake mined diamonds. We'll see if that actually ends up being true. I may be learning stuff right now as you're listening to this. While I'm down in Tucson, I'm taking some seminar classes. Maybe I'll learn some more things and I'll let you know about market share. And then finally, we have impact formation diamonds, which maybe could be called catastrophic diamonds or something like that, because they are from a meteorite smacking into the earth. Okay. And we don't really mine diamonds from those. They're too small and they're too widely dispersed. And we'll talk about those. All right, let's talk about synthetic diamonds or lab-grown diamonds, not mined, cultured, lab created. I mean, there's a gazillion different ways to talk about it, but these are non-mined. They are not naturally forming in the earth. Diamonds that are made in the lab. They are considered real diamonds because they have the same chemical properties. They are made out of carbon. They have some impurities that are the same impurities that we see in natural diamonds. They have the same optical properties. They are isotropic. They have high indices of refraction. And they have the same physical properties. They are the hardest substance known to man. They have the same crystal structure. They have cleavage, just like all regular diamonds. So here are some examples of a CVD diamond, an HPHT diamond, and an HPHT diamond and a natural diamond right here. Hopefully you can see, hopefully it's recording what my pointer is doing. All right, so now that you know this, there's a couple of other things you need to decide. You need to think about. Synthetic diamonds are priced at about 10 to 20% of natural diamonds, which is crazy. And the reason why it's crazy is because um, when I first started teaching this class, it was like 60 to 70% natural diamond. I mean, synthetic diamonds were worth about 60 or 70% of natural diamonds. And so there you go. Now, synthetic diamonds do not have the same environment or ethical concerns as natural diamonds. That doesn't mean that they don't have environmental and ethical concerns. It simply means they don't have the same ones. And synthetic diamonds are virtually identical to natural diamonds. If somebody came out and put out their hands to you and said which one is synthetic and which one is natural, you, by visual examination, would not be able to know. You'd have to use laboratory tools. So the question is would you buy a synthetic diamond over a natural diamond for your engagement ring? And maybe some of you have already made this choice. All right. So let's talk about where this all starts, okay? It's not until the 1950s that we actually are able to have the technology to actually synthesize a diamond. There is a gentleman by the name of Tracy Hall. He worked for General Electric, and in 1954, he was part of a team that was asked to try to invent a way to make synthetic diamonds. And they weren't thinking for diamonds for like jewelry, they were thinking for like industrial use. And so he's part of this team, but apparently it was a lot like a lot of group projects in that one part of the group wanted to do it this way and he wanted to do it a different way. So he kind of went off on his own and did his own thing in this group project. And he created what is known as a belt press. And this is an example of a belt press. And it actually was able to get heated up to 2000 degrees C and create about 10 gigapascals worth of pressure. And what Tracy Hall did is he put graphite in there and he dissolved the graphite in molten metal. So, like, he melted a whole bunch of iron and stuff like that and dissolved the graphite in it, squashed it really hard, and made the first created diamond. It was 0.15 millimeter in size and it was not gem quality. And yet, this is the very first time that that somebody has created a diamond. Now, there's actually an exception to this. Interestingly enough, there was a team in Sweden who was working on something very, very similar. Didn't know anything about Tracy Hall or anything like that, but they were working on something similar. And they actually figured out how to create a diamond a couple of months before, like a few months, I don't remember if it's 6 or 10 or something like that, before Tracy Hall did it. But they were working for this super secret laboratory for the government in Sweden. And so they weren't allowed to tell anybody. And it wasn't until like the 1980s that it was discovered that they actually beat Tracy Hall by a couple of months. And but because Tracy Hall was allowed to publish it and to talk about it, and GE made a big deal about it, he's considered the first person to make a synthetic diamond, even though these other guys were the first people, really. But you got to publish. You got to publish. Anyway, Tracy Hall wasn't thrilled about GE, and he made this amazing thing for GE, and they gave him like a $20 gift certificate to the cafeteria or something. Said, "Hey, good job, dude. You did what we asked." And they didn't treat him very well, so he left GE in 1955, and he goes somewhere else and actually keeps working on this idea. Now he can't use the same idea because this was owned by GE, because he was working for GE when he did it. But what he actually ends up doing is he ends up going to this other place. He actually changes things, and he develops what's known as the tetrahedral press. Now the tetrahedral press actually comes at whatever it is in four different directions. And because it's coming in four different directions, it is able to more easily create the pressure and the temperature that is needed. Now, where does he do this at? Because it's going to blow your mind, because you've all heard of this place, okay? He goes to BYU. Yes, indeed. He was a physics professor at BYU when he figured out how to make the first tetrahedral press. And this tetrahedral press is the same basic type of press that everybody in the whole world uses to make HPHT diamonds. So to make the high pressure, high temperature diamonds. So actually this picture right here on the right, he is in the basement of the Eyring Science Center, and this exact location, my friends, is where our lab is today. Now, it's a completely different setup, and they've totally torn down a bunch of walls and put in new walls, but these exterior walls are the same ones that are in our lab, which is so cool. Anyway, I just think that's fun. And here's the lobby of the Eyring Science Center, but they displayed his first tetrahedral press for a really long time. His favorite thing was to take somebody's peanut butter sandwich and actually use that as the source of carbon so that he could make a diamond out of it. So that's what the Skippy peanut butter is for. Because really, all you need is some form of carbon, and you can make a diamond out of these types of things. So let's talk about diamonds and their stability field, and how can we create that here on the Earth? I mean, on the surface of the Earth, instead of going really, really deep. Well, there's two main types of diamond formation, lab formation, and it's high pressure, high temperature synthesis and chemical vapor synthesis, deposition synthesis. Now, there are two others called shockwave and ultrasound, but those turn out to not be very economic. So we're just going to say, hey, they exist, but we're not going to really talk about them because nobody's using them to create diamonds right now, except for in laboratories doing experiments and stuff like that. So let's start out with high pressure, high temperature. So high pressure, high temperature diamonds, HPHT, you have to have a lot of heat, hence the high temperature. All right, it's pretty much as hot as basaltic lava. So if you've ever been to Hawaii and seen the volcano erupting and it's super, super, super hot, that's how high the temperature gets in those tetrahedral presses. You also have to have extreme pressures. We're talking about 5 gigapascals, which is huge. 1 bar of pressure is where we are today here. I mean, we're actually a little less because we are at a higher elevation. But if you were at sea level, that's 1 bar. This is 50 kilobars, and a kilobar is 1,000 bars. So that's what 5 gigapascals turns out to be equal to. And basically, it's as much as 80 elephants stepping on one of your toes. And they're all stepping on that one toe at the same time. I actually don't know how that would work, but you get the idea. Now, how long does it take for a high pressure, high temperature diamond to form? Well, it takes between days and weeks. It's not a really long process, actually. It's pretty fast. And this is an example of some of the stuff that comes out of these high pressure, high temperature presses. Now, at first, it was really hard to exclude enough nitrogen to get something that was colorless, but pretty much now we've gotten really good at it, and this is what comes out. It used to be that all HPHTs were type 1b because of the nitrogen. But now we've been able to exclude the nitrogen to the point that they are type 2s. And then we can actually add other stuff into them and make them other colors too. So basically, this is what happens. Here's a bunch of these tetrahedral presses. This is in China. This is a factory in China. Each one of these is a tetrahedral press. And inside each one of these, this is essentially what it looks like. You have to have a little seed crystal. You basically have to teach the graphite how to grow. And then you have this metal flux. So you have liquid metal, just like Tracy Hall did. You have your heated element, and then you have your carbon source. And what happens is that the growth chamber is heated and pressurized, and the molten metal dissolves the carbon from the carbon source. And then the carbon atoms move through that molten metal and start depositing on the seed. They start to precipitate, they start to become solid. And this is what it looks like when they come out. Now, the really fun thing is just like I was saying about Tracy Hall, you can use anything that has carbon in it to make a diamond. So you can use grandma's ashes. You can use Rover's, your dog's fur or whatever. And we're not going to watch this video, but you're welcome to go watch it on your own. It's just kind of a pretty music in the back where they're showing you how they're doing it and everything like that. But basically, these are called memorial diamonds. And so you can seriously take some fur from your pet and make a diamond out of it. You can take, your grandma's cremains and make a diamond out of it. The only difference between natural diamonds and memorial diamonds is their origin. The carbon atoms of memorial diamonds are from the cremated remains instead of minerals found underground. Okay, kind of fun, kind of expensive. Diamonds, lab created diamonds have gone way down in price over the last 10 years and have not necessarily gone down in price very much if you're talking about these memorial diamonds. So here are two examples of two places that I found. We're talking, $3,500 for a very small diamond, 15,000 for a 1 carat. I would probably go with Everdeer because they're, only $6,000 for a 1 carat diamond. $6,000 is a lot of money still. Maybe not as expensive as burial. Okay, never mind. Anyway, moving right along. When we first started seeing HPHT diamonds in the marketplace, and this is, we're talking like not that long ago, 2007. Some of you guys that you were already alive during that time. Most of you guys probably were alive during that time. So anyway, I just want to show you the color distribution. At first, we were not very good at it. We got a few little green and blue, some oranges. Mostly everything that came out of the HPHT was kind of a yellowy color. And then every so often we would get some colorless and some pinks and reds. But I want you to notice what happens through time. And as we get to 2023, which was the last bit of information I could find of a chart that looks like this, we're noticing that almost everything that comes out of here is colorless. And what isn't colorless, we have a little bit of near colorless. Then we have some yellows and some blues and some greens. Very popular colors, those blues and those greens. And so we've gotten very good at making pretty nice looking diamonds out of HPHT. The largest HPHT diamond was as of right now at least 129 carats. All right. It took about 400 hours to grow, and the growth speed was about 65 milligrams per hour, which, who knows if that's really, really fast or slow. It's pretty fast, actually. But it's not the prettiest thing in the whole wide world because they were trying to get it to be really big rather than trying to exclude everything else. Previous winner of the biggest HPHT diamond, we get this other big fancy vivid orange one. And this is what it looked like before they cut it. Because remember, you lose half your weight when you're cutting. So, but HPHT makes some absolutely gorgeous colorless diamonds, and that's a very, very popular type of diamond to buy. Let's move on to chemical vapor deposition. So chemical vapor deposition are almost always type 2A. And you'll remember that type 2A diamonds are rare. I mean, they're usually like the super deep diamonds. They're the really, really great looking diamonds, right? Well, we can make them now. So this is chemical vapor deposition. Basically what it is it's using microwaves, not like the ones that are in your house, but same principle, to create diamonds. So it's under normal pressure. You don't have to have extraordinarily high pressure. The heat is called semi-high heat, 900 to 1200 degrees C. It's still really, 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 really hot, but it's still not as hot as the other ones have to get. These do take longer to grow. Okay, we're talking weeks to months rather than days to weeks. But basically this is what it looks like, okay? You have these little seed plates and you can actually do a whole bunch of little diamonds all at once with CVD. You have a vacuum chamber, you fill it with gas that has carbon in it. The chamber is heated up, and then this microwave beam that kind of looks like Darth Maul's lightsaber goes through and actually causes the carbon to precipitate, to become solid out of the plasma, and it deposits on the seed plates, the seed crystals. Now, both of these two different types, the CVD and the HPHT, they both needed to have some kind of a seed crystal to help. And that's really normal. You have to basically teach. I mean, you're not really teaching, but you're giving an example of the carbon to how you want it to grow. And it's easier to grow on something that it has a template for. Now, obviously, in the beginning, those seed plates were real diamonds, but nowadays they're not. They're absolutely just, they're synthetic diamonds. You just grab another synthetic diamond and put it in there and have it be the seed plate because it doesn't matter. You just need a diamond. Um, the color distribution of CVDs has actually been a little better for what we expect to see in a diamond because most, at least, even at the very beginning, you were getting colorless diamonds and then you were getting almost colorless diamonds and then you were getting pretty pink diamonds. And so that was popular as well. But as you can see, we're getting better and better at doing colorless as we can learn to exclude the other things we don't want to have. The world's largest lab-grown CVD diamond is 75.33 carats. And this was actually, it hasn't been beat yet. This was back in 2024, but as I was looking yesterday, this hasn't been beat yet. And it's called the Celebration of India, and it was grown in India. So that's why they called it that. And it's gorgeous. It's absolutely beautiful. The other fun thing that can happen with CVD diamonds is, and actually, to be honest, you can do it with HPHT. I just didn't find it even from that. But you can make a solid diamond ring. You can get a largest piece of diamond and you can carve a ring out of it. And so this is one diamond that would be a ring. Now, I'm going to be honest with you. When I was looking at Etsy today, because that's where this is from, I saw this identical picture in like 4 different shops at different price points. Take it with a grain of salt. I'm not sure I'd be running out to go buy it right now. But $9,700 for a solid diamond ring. Do you know what my biggest worry would be with that though? What if I smacked it on like the desk and I hit the cleavage point? I do think that that's a possibility, and I would be scared to do that because that would be $10,000 that was just gone. Anyway, they're kind of fun and silly. So let's talk about synthetic versus natural diamonds right now. So these are some data that I found just in the last couple of years. It's not up to date, and there have been a lot of changes. I just haven't been able to find any that is up to date more than 2019 and 2021. But this gives you kind of an idea. So this is the market share of man-made gem quality diamond production. So this is of all the gem quality of all the gem quality synthetic diamonds that are being made, who's making them? And it's China and India and Russia, Singapore, and the United States. Okay, so this was in 2019, but the large majority of synthetic diamonds are coming out of China. Now, remember what I told you about how synthetic diamonds don't have quite the same environmental and ethical concerns? Well, this is one of those ethical concerns, okay? So if we're getting most of our lab created diamonds from China, is that something you're comfortable with? Are you, considering all of the unethical things that China does? And so those are some of the things you have to think about. It's not that a lab created diamond has no problems whatsoever. It's just that it has different problems. Also, creating diamonds takes a huge amount of electricity, whether it's HPHT or CVD, it does not matter. It takes an enormous amount of power. And so then you have to start considering greenhouse gases and you have to consider water usage and things like that. So, there are real ethical concerns in both directions. I'm not trying to say there aren't. There are. But just so you know, a lot of people are like, oh, I got synthetic because I didn't want to support blood diamonds. I'm like, yeah, but you're supporting China. So did you think that through? It's not that I'm saying one is better than the other. I'm just saying you be aware of what the things are. This is showing you where our natural diamonds are coming from. And so then you also have to ask a question. Hello, Russia. So that's something you need to be concerned about. Okay, but oh, Canada's not so bad. I don't hate Canada. Botswana's not bad either. So we've got some other places. But on the other hand, you also have to be concerned about the environmental cost of digging up tons and tons of dirt to be able to find one diamond. And so there are concerns on both sides. And I mean, I actually don't know what's going on with Angola right now, but last I read, it wasn't great. They don't have the best government and stuff like that. So once again, you do have to be concerned in both directions. Can we tell synthetics from naturals? Absolutely, not even a problem. We've got that figured out. Now, caveat, we can't do it just by looking at them, okay? You cannot tell just by looking at them. You generally are going to need a microscope that has UV light, or you need to have a cool, expensive testing device. So this particular expensive testing device is so awesome. I got to play with one once. It was so fun. It's only $5,000 and we don't have one. But basically, it tests them and it's actually testing what kind of impurities it has and what its fluorescence is doing. And it will tell you to either, yes, this is natural, or you need to look at this harder. Okay. It doesn't actually say this one is synthetic. It says go look at it more. Um, what it's looking for is basically there's different growth that's going on. A diamond itself takes millions of years to form underground. So it's going to be under different pressures and it's going to be growing in a different way. And so one of the ways that we can look at it is we can actually look at very minute differences in some in the way the light is being absorbed in a natural diamond versus an HPHT synthetic. Do you see this crazy big dark spot? And then in CVD synthetics, it also has a very different look. And so we can actually say, oh, hey, this was a CVD. So if we see something that looks like these funky little lines, then that's a CVD. Or if we see stuff that's looking like this weird kind of sorry, lost my train of thought, this weird type of hexagon, then that's going to be more likely to be an HPHT. And then the natural is going to have this nice look to it. So those are some of the ways we can tell. And here's just some pictures. There's some really interesting things that you can see with some diamonds. But this is all under microscopes with special deep fluorescence and stuff like that. If you have it on your fingers, nobody's ever going to know the difference. Okay? How would they know? So, when you go back to that first question that I asked you, do you think that we should do you want to buy a synthetic or a natural diamond for your engagement ring, perhaps? Let's talk price. Okay, so right now, today, if you go buy a 1.02 carat round lab grown diamond that has a GIA certification on it, and it's D color, VS1 clarity, excellent cut. You will only pay $770 and it will be here for Valentine's Day. Just, in case you needed to know, right? If you buy a slightly smaller diamond that's real, rare, natural, D color, VS1 clarity, excellent cut, so very same parameters, just a little tiny bit smaller, you're going to pay $4,600. And maybe it'll be here. Says like it'll probably be here by Valentine's Day. That is a almost $4,000 difference. So it's kind of going to have to be a decision that you and your partner make, especially with an engagement ring, about what you want to do. Okay, there's lots of options out there, and I'm not telling you that one is better than the other. I'm just telling you what it is, what's out there. Now, that was synthetic diamonds. Let's talk about these extraterrestrial diamonds or these catastrophic diamonds. And the reason why I call them catastrophic diamonds or extraterrestrial diamonds is because they're literally being formed because of something coming from outer space. So there's this place in Bavaria, in Germany, called Nordlingen. And the Nordlingen Ries, I'm sure I'm pronouncing that exactly right, but the Nordlingen Ries crater is this large crater that you can see right here, and it has the town of Nordlinger in it. Now, this makes it look like this is the size of the town. It's not. This is just a normal walled city, medieval walled city, okay? It's also round, but it's not sitting in the crater. The crater is much bigger than the city. Anyway, this is a crater that was formed when a meteorite smacked into the Earth 15 million years ago. Now, the crater itself is 24 kilometers, and the meteorite we estimate was about 1.5 kilometers in length, and it had the power of 1.8 million times the Hiroshima bomb. When it hit, when it hit 15 million years ago, it hit a local graphite deposit. And what is graphite? Graphite is just carbon. And so the shock and the pressure and the heat and the graphite all together created itty bitty little tiny diamonds, about 72,000 tons of them. That's a lot of diamonds. That is 326 billion diamonds. I mean, billion carats worth of diamonds. The one problem is they are so small, okay? Each one of them is smaller than 0.2 millimeters. Just to give you an idea, you guys have all done the thing where it's like your faith, if you had faith the size of a mustard seed and all that stuff, mustard seeds are bigger than that. They are between 1 and 2 millimeters, okay? Here are salt grains. They're bigger than these suckers are, okay? This church right here is actually made out of diamonds. All right, like inside of this rock, this is a what you call a breccia, an impact breccia. It's the broken up rocks from that big massive thing. It has teeny tiny diamonds all throughout it. And it has 5,000 carats worth of diamonds in here, and every single one of them is too small to do anything with. But what a cool church to go to. I go to the Diamond Church. That'd be actually really fun. What other types of extraterrestrial diamonds are there? Well, in our big gas giants, Jupiter, Saturn, etc., they have very thick atmospheres that are made out of methane, and methane is carbon and hydrogen together. And it turns out that when there's lightning, and there is huge lightning storms on these gas giants, it actually will separate the methane molecules into their constituent atoms. When that happens, the carbon is under so much pressure, and it's really, really hot in these gas giants. It's under so much pressure and so much heat. We believe that it hits the diamond stability field. And so we believe it's possible that it rains diamonds on Jupiter, on Saturn. Okay. So these are some of the possibilities that are out there. It would be slightly painful. There's also the possibility that there are whole planets made out of diamond, which is just insane, okay? But basically, what you would need is you'd need some water, some heat, some pressure, and some carbon. And boom, you could have diamonds, and you could even have diamonds be as common as the rocks that we have today. So, like a whole mountain of diamond. You would have diamonds in your yard. You would have landscaping diamonds, and you would have diamonds that you use in your sandbox or whatever. Okay. We're not 100% sure that that's what's going on, but it's a possibility. We've got the right conditions. We don't know if it's actually forming them. So watch this space. Who knows what we're going to discover? So we've talked about diamonds, and we've talked about different types of diamonds, and how they can be formed, whether it's in our labs or in space or from a meteorite and stuff like that. Now let's talk about things that aren't diamonds, but are pretending to be diamonds. And these are called diamond simulants, okay? A diamond simulant, a simulant of any kind. So you can have gemstone simulants all over the place. It's something that's imitating something else. So for example, if I have a piece of glass and I say, "Ooh, look at my diamond," all of a sudden that's a diamond simulant, okay? I am pretending it is a diamond. Rhinestones, for example, are diamond simulants, or if they're colored, they're another gemstone, ruby simulants, sapphire simulants, whatever. Remember that when we're talking about simulants, we are not talking about lab-grown diamonds, okay? Lab-grown diamonds are actual genuine diamonds. They are synthetic, not the same as simulant. Simulant is fake, synthetic is made in a lab. Um, you can actually have a true gemstone, like a piece of quartz. That's a true gemstone. You can have a piece of quartz and you can have that be a gemstone simulant. It's only called a simulant when it's pretending to be uh, a different gemstone. So we're all familiar with gemstone simulants, diamond simulants, whatever. I mean, how many of you have played with those big plastic gems and rhinestones on Elvis's jacket? Those are all gemstone simulants. So this is not something that is unusual for us. So let's talk about them. There's a number of different kinds. Some of them are pretty good at simulating a diamond, and some of them are really bad. So first, we're going to talk about the ones that are real gemstones. Um, wow, I just lost my. Okay, we're going to pause for just a second, maybe. My computer is crashing, so we're going to try something really quick. And okay. I think we're back. That was really weird. I apologize. I do not know what happened with my computer, but it just shut my PowerPoint down completely. What were we talking about? Diamond simulants. All right. So diamond simulants that are the ones that have been used for the longest amount of time are the ones that just are naturally occurring. So for example, quartz can come very colorless, and so that can be called a diamond simulant. In fact, they actually would pick up pieces of quartz from the banks of a river in Europe, and they were very, really nicely clear. And so they did look a lot like diamonds. And so they started selling them as diamond substitutes, and they called them rhinestones because they were picking them up from the River Rhine, the banks of the River Rhine. And so that's where true rhinestones start out as. Now most rhinestones are made out of glass or plastic, but back in the day they called them rhinestones because they were picking up quartz from the banks of the Rhine River. Now, the thing about quartz is it's not as hard as a diamond, so it's going to get scratched. And it doesn't have as good of an index of refraction, so it's not going to be as shiny. So here's your diamond example, and here's your quartz. Not the most convincing thing in the world. We can move on to something called zircon. This should not be confused with cubic zirconia. Zircon is a naturally occurring mineral, all right? So all three of these are naturally occurring minerals. When it is colorless, it can be used as a diamond simulant. And it's not bad. It's got a pretty high index of refraction, but its hardness is not that great. So while it's shiny and pretty, it scratches easily. Topaz. We're going to go get some topaz near the end of the semester at Topaz Mountain. It comes colorless. In fact, most of the stuff you're going to be picking up will come colorless. The hardness is pretty good at 8. It's not fabulous, but it's not bad. But the index of refraction just isn't really up there with diamonds. So these were fine, but they weren't fabulous. So then we move on into the technological revolution, and we start with glass. We discover that as you are adding more and more lead into your glass recipe, you actually can get a shinier and shinier piece of glass. So this isn't window glass. This is what's known as flint glass. And so these types of things have been used to be a gemstone simulant since the 1600s. So a really long time. Oh, 1700s. There it is. It says so right there. About 1758 and onward. So flint glass, this is a manufactured thing that we are now starting to use as a gemstone simulant. Not the most fabulous, but really cheap and really easy to make. Starting in about 1900, actually the late 1800s is when they figured out how to do it, but it doesn't start being commercially produced until the 1900s. We get what is known as synthetic sapphire, and that's literally sapphire that they make colorless. It is hard. It's 9 on the most hardness scale, so it's nice and hard, but it just doesn't quite get up there with the index of refraction. I mean, it's better than glass, but it's okay, okay? We still use synthetic sapphire as diamond simulants. As the technological revolution continues, we are able to start creating some other things that are naturally occurring but don't occur looking like this. So rutile is an actual mineral, but it only ever appears in little teeny tiny things. And so it never gets big enough for you to facet. But we discovered how to start making it, looking for different things to use for lasers. Okay, so this is in the 1940s and 50s, and we're trying to do lasers. And so look at how high this index of refraction is. It is higher than diamond. So it is super shiny and pretty. Problem is it's super, super soft. And so it has a very short lifetime as a diamond simulant. You just do not find this unless you are looking at vintage jewelry anymore. However, we keep persevering and we keep trying to make more stuff. Okay. We strontium titanate. Okay. So strontium titanate is another man-made object. And it has a gorgeous index of refraction right there with diamond. It's not very hard. That's the problem with it. So it's really shiny and it's actually super, super, super shiny. It has high dispersion. The problem is it's almost too much. It kind of looks like a disco ball, so it doesn't really read as a diamond. There are two garnet forms. Now, these are both synthetics. They are not naturally occurring ever. But we have these two. It's YAG, which is yttrium aluminum garnet, or GGG, gallium gadolinium garnet. And these were popular for a very brief amount of time in the 19. This is wrong. I've got something wrong here. Sorry about that. This should say the 1970s as well. So these are both in the 1970s, and they're good, but they're not perfect. Like the hardness really isn't right where it should be, and they don't sparkle the same way. Now, of course, during this time, we start using plastics, and I think you've all seen plastic diamonds before, probably familiar with these guys. It's plastic, so it's really easy to know what it is. But like the index of refraction is terrible. It's really soft. I mean, it's plastic, okay? But that's another diamond simulant. Now we get to the ones that you're probably familiar with, okay? Cubic zirconia is probably the one that you have heard the most about. Now, cubic zirconia is let me try that again, synthetically made, but the thing you have to remember is that it actually does occur naturally, but only microscopically. So none of the CZ, none of the cubic zirconia you see in jewelry is ever natural. It's always man-made. So cubic zirconia is actually zircon and oxygen. It's got a pretty nice index of refraction. It's not doubly refractive, so that's good. It's got great dispersion and stuff like that. One of the biggest problems about it is its hardness. Now, you might think 8.3 is pretty hard, but when you're wearing something on your hand all the time and you're banging it against stuff, you're going to bang it against stuff that is going to scratch it, unless it's a diamond. And so the more scratches you have on your cubic zirconia, the less it looks like a diamond because it starts to look dull and greasy. And so cubic zirconia is fabulous. It's a great idea in jewelry, but not something that you're going to wear every day unless you're willing to replace your cubic zirconia every 5 years or so. Then you could get away with it. How does cubic zirconia get made? It's really fascinating. We didn't figure out how to do it until the 1970s because it's got to be, it's what you have to do is called the skull melting method, which it just makes me happy because hello, skull melting method. It's actually not that. But basically what it is, it was developed in Moscow. Cubic zirconia's melting point is way too high. It is so high that you can't find something to melt it in. Like even a platinum crucible can't get that high without melting. So what happens is they actually put zirconium and some stabilizers and stuff are in a crucible, and then they heat it up, but before it gets too hot, they actually cool the outside of it. And that makes this kind of a rind or a skull, which then can actually hold the melt. So then what you do is you take it out of the, you let it get really, 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 really hot. You take it out, you let it cool, and then you smash it with a hammer, just like Yzma. And what you end up doing is you end up getting pieces of cubic zirconia out of it. And I've had students tell me that this looks like brie cheese, and it sort of does. So it's forbidden brie. And depending on what additives you put into it, you can have all different types of colors. So cubic zirconia is awesome, just not as durable. The next one that you've probably heard of is moissanite. And moissanite did not come onto the market until 1998 as jewelry, as a diamond simulant. It also occurs naturally, but only microscopically. Okay, so it's very, very microscopic. All the moissanite, that should say moissanite. Goodness, there's too many mess ups here. All the moissanite in jewelry is man-made. Okay, it's a synthetic. It's made out of carbon, but also silica. Okay. Great index of refraction, pretty good hardness, and super cheap right now. Okay. People are not buying moissanite very frequently right now because they can buy synthetic diamonds. And so if you want moissanite, you can get it for super cheap. I picked up two 1.25 beautifully cut moissanites at Tucson a couple of years ago for like $100 each. So it's crazy cheap. So it's not a bad idea. Moissanite isn't always gorgeous like it is here. When we're just making it into the crystals, we've actually been doing that since 1891, trying to make synthetic diamonds. But these were only used for industrial uses, but they have so many good industrial uses. You know, like they're used in automotive parts for Tesla. Okay. They're used in computer chips and composite armor and stuff like that. So moissanite's a pretty cool element. All right. So how are you gonna know whether the thing that you just picked up is a diamond, a synthetic diamond, a simulant, it's a piece of glass, whatever it is, okay? Well, I mentioned this before when we were talking about the thermal properties of diamonds. You can get a diamond tester for 16 bucks on Amazon, but you gotta be real careful about it. These are working on the thermal conductivity of the stone. And the thing is it will distinguish between diamonds and everything except for moissanite. So it can't distinguish between moissanite and diamond because both of those are highly thermally conductive. It absolutely won't tell you the difference between a synthetic diamond and a mined diamond. For those, you have to get the super expensive ones. So if you're wondering, how are you going to figure this out, seeing as you don't have these things? If you can pry the stone out of the setting, then you can figure it out because the specific gravity of each of these is different. However, most people don't let you pry the stone out of the setting very frequently. So otherwise, you're going to look for scratches. You're going to look for weird dispersion. You're going to look for rounded edges, fractures in it, doubling facets. And we'll talk all about these in lab in different points. But really, one of the best ways to look at it is just to look at the price. Because if it's cheap, it's probably not a real diamond. So, all right. Thank you so much for your attention. And that is the end of this particular one. And then I will record the next one, and I'll see you when I get back from Tucson.